Hello, everyone. I hope you are all enjoying the conference as much as I do. I was so much looking forward to be with you, discuss with you, learn from you, hear about all the projects you are building, the amazing stuff you are contributing to, learning from you, and discovering all the awesome stuff you are building. But unfortunately, things happen. And I hope you are all safe and healthy while watching and enjoying the conference. This is the last day and probably the last conference session of the conference. I want to thank the G Point team for the amazing stuff they did putting out this conference together. They made it look pretty easy, but believe me, it isn't. Those guys succeeded to make a virtual event a success, even with all the challenges a virtual event comes with. So thank you guys. Thank you for such an amazing conference again. So back to my session, and my session will be about service mesh, and we will discuss what is service mesh. Do I need one? What challenges it comes with? What is the journey that brought us to think about service mesh and the sidecar pattern and all those kinds of stuff? But before jumping into the technical part, I want to start by telling a story. So just bear with me while going to the technical part, but just I want to highlight some fun stuff with this story. So, and the story I want to tell you is about the phone. So, the phone was basically invented by Graham Bell, and the first phones were primarily point to point communication, and they were rented in pairs, which limited conversation only between the parties operating those instruments. This, as you may think, didn't actually scale well, and the use of a central exchange was soon found to be more advantageous and enabled better scaling. So, in order to allow multiple humans to talk to multiple humans at any given point in time, it were necessary to build some sort of interconnection between those phones. And we started using switchboard and switchboard operators. And the job of those operators were basically to manually route traffic and route incoming traffic to their destinations. So the journey was in order to make a phone call, I would actually pick the phone not during the person I want to talk to, but actually call an operator and tell that operator that I want to talk to someone, and she afterward would then connect me to the person I want to talk to. And the further the call I want to make, the more operators I had to talk to in order to get there. This scaled for some time, but didn't scale very well. More lines meant more switchboard and the need for more operators, and thus this means we need more expenses. And to actually solve this problem, we had to move away from the manual aspect of human interfacing and move to a more automatic exchange, as you can see in this slide, and even go beyond that to a more digital interconnection where everything is routed automatically. And you may be now wondering why I'm telling you this story in the middle of a technical session. And that's because I believe we, as software developers, are following the same journey when it comes to the way we architect our applications. So, the first applications were monolithic applications, simple flow of communication, but it didn't scale well. And in order to scale, we started to break this monolith into multiple applications. And we started to have multiple challenges when we went to distributed systems. And we invented some solutions that didn't help us very well to solve the infrastructure challenges that come with running distributed systems, especially at scale. So this is what this whole talk is about. And this is the boring slide. I am Mohammed. I work for a DevOps company in Morocco called XHub. I am very active on Twitter. So if you want anything related to Java, microservices, containers, or everything in between, I'd be more than happy to discuss it with you guys. And if you are not a Twitter person, this is my email. Please feel free to ask me about anything. Feel free to send me your feedback, even about this presentation. I'll be more than happy to read your comments. So yeah, let's move to the fun stuff. So let's actually go back and analyze the journey of our application. I know this is getting a lot more about history, but just bear with me, we are getting there. I believe that understanding the path we took help us to understand better why we made some decisions and help us to understand better the solutions that we are talking about. So in the 90s, this is how the majority of our applications looked like. It was monolith application and single language. All components of an application are assembled together and tightly packaged. There were a simple flow of communication between the client and the server. But the problem, if you wanted to scale, it was really complex and really hard. And scaling was going to hit you hard and probably really hard. So, in order to scale, we started to break the monolith into multiple components and multiple services. And those services communicated with each other, and the communication can involve either passing simple data to between those services, or it could evolve two or more services coordinating some activity. Some means of connecting services to each other was needed, and we used some kind of smart pipes like enterprise service buses and message brokers. And enterprise service buses reigned as the preferred method for connecting monolithic business applications. The promise was legit, as you can see in the slide, and even it seems some of the things that we are trying to solve and trying to do with the newer technology that is cropping up. And this is just to say that the challenges that we are facing nowadays are not necessarily new challenges. Those are kind of all new challenges that we try to solve in the past. And in 2010, 2010 has been basically about making everything smaller. We move it toward dump pipes, we move it toward decentralized communication, we use it multiple languages to build our services and applications. It helped us to make our team more cross-functional and general purpose. It enabled us to deploy faster, deploy smaller, and deploy better. And you probably heard about some success stories of many companies that managed to adopt or build a distributed system at scales using microservices architecture. Probably you heard it before at this conference or probably in another conference, and they are all preaching how they successfully managed to deliver value using microservices. But the problem with this architecture is the more services you have, the more complex the system becomes. And we started to have some all new challenges, but this time at scale. So let's explore one of those challenges. So this is a very typical microservices application, and let's consider these two services here. Let's call this one X, and let's call this one Y. So Y X. So service X is dependent on a third-party service, which is Y, and service Y become unhealthy. So every request from X involving a call involving a call to Y increases response time to X as X keeps calling and calling and calling service Y repeatedly without handling the failures that were happening, which basically led to an increase in CPU usage for X and a decrease in the number of free threads to process other requests, which eventually lead to service becoming unresponsive. And the same thing happened with other services that were relying on X to deliver some functionality, and the failure was cascading and cascading and cascading until your whole application become unresponsive and your whole application is, and the small problem that started at the service Y brought your whole application to its knees. And this is how we look like as developers and operations, trying to understand what is happening, trying to figure out why our system is becoming unhealthy, and trying to bring our application back up again. So this is to say that there are a number of moving components and moving parts in a distributed system, in a microservices architecture, and thus there are more points of failures. And the thing is, distributed systems, especially the one at scale, follows Murphy's Law. And Murphy's Law basically says anything that can go wrong will go wrong. So the more instances of anything we have, the higher the likelihood that one or more of them will break. Probably they will break at the same time. There are things that monolithic architecture guarantees that are no longer true and no longer valid when we move it toward distributed systems and microservices architecture. Services now no longer start and stop together. Services no longer start and stop in a predictable way. Services may unexpectedly restart, changing their state, changing their version, and so on. If there were no errors, distributed systems would be basically really simple and easy to use, but this is not really the case. Distributed systems are really hard. And as I've mentioned previously, those are not necessarily new problems. Those are all new problems. And the proof is more than 20 years back, James Goslin, the father of Java, and Peter Deutsche described what we call what is known as the 8 fallacies of distributed systems. And those are the fallacies and the false assumptions that we as developers make about distributed systems. So let's spend some moments and explore them by one. So the first false assumption we make is the network is reliable. But this is not true. Stuff happens, failures happen, probably in the hardware, probably in the software. There were some power supplies, routers issue, patch issues, and those kind of stuff. So the network is not really reliable. We aim to think that latency is zero. And you know that there is 7 orders of magnitude difference between in-memory calls and calls over the network and the internet. So our applications in distributed systems should be more container aware. We aim to think that the bandwidth is infinite. And we may agree that this is not generally a problem. Although the bandwidth has improved over time, the amount of data that we send and we communicate and we transfer has increased too. Think about streaming application and all the streaming videos that we saw all day. The fourth false assumption that we aim to think and we aim to believe is the network is secure. And this is one assumption that gets more media coverage than the others for obvious reasons. And the only secure system that is secure, as you probably know, is the one that is powered off and not connected to any network. So the network is not really secure. We also aim to think that the topology doesn't change, which is not true. Network topologies change all the time, especially nowadays with the rise of cloud and containers and the need for elastic scaling, which requires a certain degree of network agility. We also aim to think that there is one administrator, which is not really true, which is completely false. Of course, there is no one person that knows everything. The seventh one is the cost is zero, or the transport cost is zero. This is very related to the latency is zero. And the final one is the network is homogeneous, which is obviously not true. There are a couple of so those fallacies are discussed more than 20 years back, which highlight that the service or distributed component is hard, especially at scale. There are other challenges that we may face with distributed systems and microservices and distributed architecture. Think about observing interaction between services. It becomes more complex when you have many distributed and loosely coupled components. How about traffic management and doing things like Canary deployment, A/B testing, and those kind of stuff without impacting your clients and doing those things transparently? Those traffic management become really hard in distributed systems. Also, think about securing your communication or encrypting data flows. So this those things becomes really hard when you have distributed applications, and especially when we have applications that or services that are written with different languages. And finally, think about managing timeouts and communication failures between the services. When we have distributed systems, as we saw in the example before, this can lead to cascading failures and is more difficult to do to handle correctly when we have distributed applications. So when you consider how critical the ability to control and secure service-to-service communication in distributed systems, you understand that we are kind of under-tooled, and you start to understand that running more than a few microservices is difficult, is really difficult. And those are not new problems. Those are all new problems that we tried to solve many years ago. So we started to solve those issues and those challenges with message brokers. And we said, yes, we have this centralized set of messaging-oriented middleware. And we thought, yeah, let's add things like retries, back pressure, service discovery, and delegate them to the message broker. This approach didn't actually work well. It was quite heavy-handed. It also tends to be a big bottleneck. And the implementation of infrastructure and network aware or network functionalities in message broker wasn't as easy as we thought. Then we tried the next solution, which is we have our message bus, and we said, yeah, let's add things like routing, policy control, transformation to it. But the complexity and organizational structure wasn't really good and was an overkill. And although the intentions were good, as we saw earlier, we found that mixing core application networking functions with functions that are basically much related to business logic is not a good idea. And this approach turned out to be a bottleneck. And the third thing and the third idea came with the rise of API first mindset and the REST revolution. So with the REST evolution, we invented a new piece of software, which is the API gateway. And the gateway provided us with a centralized way of controlling outside access to our APIs. and we controlled them through security ECLs. It enabled us to define access quotas. It enables us to collect metrics. It provided better documentation for our APIs and all the benefits that comes with the API gateways. And we said, yes, we have the API gateways, so let's add some infrastructure functionalities to it. But the problem with this approach as well is we started going down the path of building another ESB, which combines infrastructure level networking concerns with business logic. And the other thing, and the next challenge that the API gateway doesn't solve is we still have problem with what we call the east-west traffic, which is the communication between our services, or the enter communication. So many companies and many organizations started to take a new approach, and they started using client libraries to handle infrastructure logic and networking concerns. And it worked really well for some organization and enabled them to build microservices at scale. But as the number of services in the system grow, they also stumbled upon various drawbacks of this approach. So the most significant drawback is the tight coupling of infrastructure concerns with application code. So these language-specific resilient libraries can be costly for some organizations to adopt wholesale, and they can be really difficult to wedge into brownfield applications, or entirely impractical to incorporate into existing architecture. So this was a brilliant solution, but it has some drawbacks as we discuss it. Then some practitioners started to think to push down application network functions to the infrastructure, and this will enable us to enable us, the developers, to focus on the business logic and avoid wasting time of infrastructure code and managing client libraries. So the idea here was simply to put and extract infrastructure logic and network concerns and put them down a layer into some networking layer. But this is, as you probably know, isn't actually possible. We can't add another layer to our networking infrastructure. But the idea, or this idea, wasn't completely abandoned. So, and what emerged was to implement the previous idea as a set of proxies. So the idea here is that a service won't connect directly to its downstream dependencies, but instead all the traffic will go through a small piece of software that transparently adds the desired features. And we call this pattern the sidecar pattern. So those proxies will live next to each application, and applications no longer need to have language-specific resilient libraries for things like circuit breaking, retries, timeouts, service discovery, load balancing, and so on. And this is how basically the service mesh was discovered, and this is how the service mesh was born. So what is the service mesh? A service mesh is ultimately not an introduction of new functionalities, but simply and rather a shift in where functionalities is located. It doesn't establish connectivity between microservices, but instead has policies and controls that are applied on top of an existing network to govern how microservices interact together. And as many companies moving toward more cloud native and microservices architecture, the path that those companies will follow differ from organization to organization. And service mesh, and this is where service mesh focus. And basically, it shifts the implementation. It shifts the implementation responsibilities out of the application and moves them into the network. And with the service mesh, what we are doing is we are explicitly separating application network functions from application code. And we are separating infrastructure code from business logic. And we are pushing it kind of down a layer. And this is important in a sense where just as microservices help decouple teams and created more cross-functional teams, adopting service mesh will hopefully help us to decouple operators from application feature development and release process, and giving operators a declarative control, as everything in the cloud native era now, we declare everything, we declare our intentions, and then the control plane will apply those declarative configuration to our infrastructure. So service mesh aims to give control to operators over how their service layer is basically running. So to sum it up, a service mesh is basically a programmable interface to observe, secure, and connect services. This means that you can declare your intentions, and as anything in cloud native era, we basically declare YAML. There are other configurations, and it's the job of the control plane to take those declarative configuration, we call it the desired state, and apply it to your cluster, and we call it the current state. So the service mesh will take care of applying your desired configuration and your desired state and match it with the current state. And the mesh, so based on this declared or declarative configuration, the mesh will ensure that your declared intentions are applied to the services and the network. And also, the service mesh aims to make the communication between the services more flexible, more reliable, more fast, and more secure. So given that services communicate with each other only through the sidecar proxy, we end up with a deployment similar to this diagram. So the service mesh is typically implemented as an array of lightweight network proxies that are deployed alongside your application code without the application needing to be aware of the existence of the proxies. So this is how let's look at two services deployed side by side with their sidecar proxies, and let's explore a typical service mesh architecture. It is composed of two components, the control plane and the data plane. So the data plane intercepts every packet in the request and is responsible for health checking, routing, load balancing, authorization and authentication, and the generation of observable signals. So the data plane is operating in band, and the service proxies are transparently inserted as I've mentioned it earlier, and they make service-to-service calls, and applications are unaware of data planes' existence. So data planes are responsible for intra-cluster communication as well as inbound traffic to our cluster, which is the traffic coming from the outside world to our traffic, and the outbound traffic, which is the traffic leaving our cluster. So we call them the ingress traffic and the egress traffic. So whether the traffic is entering or leaving our mesh, application service traffic is directed first to the service proxy for handling. So this is the data plane. And we have another important component, which is the control plane. So the control plane provides a single point of administration for service proxies. They provide policy and configuration for services in the mesh. They are basically taking a set of isolated stateless proxies and turning them into a service mesh. And the control plane basically operates out of that. And the control plane is an important piece in the service mesh architecture. Be careful to not confuse a service mesh with a mesh of services. A mesh of services is basically, and very simply, is all the services needed to accomplish the software's tasks. However, a service mesh is the management layer to monitor and control a collection of microservices. And as Zach Butcher, which is an SEO core contributor, says if it doesn't have a control plane, it ain't a service mesh. So the control plane is an important piece in the service mesh. So a service mesh basically augments but does not replace the services it does control. And I heard you by now saying, didn't we solve those challenges with containers and containers rules and containers orchestrators? And my answer is not necessarily. So containers simplify and provide generic, non-language specific application packaging and essential life cycle management for our application. However, container orchestrators, take responsibility for forming cluster, efficiently scheduling their resources, and managing higher level application contrasts. This table highlights container orchestration capabilities and focus versus service level needs that containers and container orchestrators doesn't offer. So the service mesh basically aims to answer those challenges and address the rest of those service level needs that aren't available with containers and containers tools. And keep in mind that service meshes are not necessarily about microservices. Not all applications are a good fit for containers and Kubernetes. So non-distributed monoliths, and that's my belief, non-distributed monoliths will be around for a long time. And service meshes will help in their modernization and can provide facets to facilitate evolutionary architecture. So whether running monoliths or microservices, service mesh will definitely help. However, keep in mind that the more services you run, the greater the benefit. So the more services you had, and the more challenges you will face, as we discussed it throughout the previous slides, and the more the benefits and the more the goodness that you can check out from service meshes. But it's not only about microservices. And these slides show some implementations and some solutions for service mesh, and shows the service mesh ecosystem that is rapidly growing and rapidly changing. And what solution you may opt for depends heavily on your need, whether or not you want it to be open source or commercial, whether or not you want it to be part of a foundation or not. So the choice of a service mesh depends heavily on what you are looking for and what are your needs. So yeah, let's talk about service mesh features. And service meshes provides visibility, resiliency, traffic management, and security control for distributed applications. So much value is promised here, particularly to the extent that much is begotten without the need of changing our application code. So the promise of Service Mesh is we can benefit from all this stuff without almost changing our applications. So let's discuss them one by one. So the first one is traffic management, and Service Mesh can provide a dozen array of features that allow you to direct traffic or to direct network traffic around your applications. Things like blue-green deployments, Canary deployments, A/B testing, and those kind of stuff becomes a lot more easier with Service Mesh than implementing them by your own. Another feature of Service Mesh is resiliency. So resiliency features typically include circuit breaking, latency-aware load balancing, eventually consistent service discovery, retries, timeouts, deadlines, fault injection, and all those kind of stuff. And Service Mesh can help you to achieve those things without much hassle. So when we talk about load balancing, till very recently, not very recently, but yeah, when we talk about load balancing, the first thing that comes to mind is round robin, but there are many things that we can do with basically load balancing. So when we talk about GBOS, it was kind of it was only round robin that was easier to implement. But now with the Service Mesh, we can have fun implementing even more complicated and more advanced around load balancing strategies, and we can see some of those stuff in the demo very soon. Yeah. Another important feature of the Service Mesh is security, and most service meshes provide a certificate authority to manage keys and certificate for securing service-to-service communication. Without, we can do things like service-to-service authentication using mutual TLS and secure connections that are established between the proxies. We can define policies that can be used to ensure that only specific services can talk to each other, which in turn allows more sophisticated security policies to be defined and enforced. And the final one, and the most, in my opinion, most important one is observability, especially for microservices and distributed systems. And observability can include logs in the forms of events and errors, traces in the forms of spans and annotations, and metrics in the forms of histograms, gauges, summaries, and counters. So service meshes largely provide black box monitoring for of your service-to-service communication. And it's time for the demo, and I will be using SEO for demoing some service meshes capabilities. And you may be wondering why I choose it, or why I choose an SEO is based basically on the CNCF survey of last year. And as you can see here, SEO was the most one that many developers were evaluating. So I said, probably many of you were evaluating SEO as well, and I wanted to provide the demos using basically SEO. So yeah, let's, okay, my keyboard isn't working. Yeah, okay, so it's connected now. So yeah, my demo will be a microservice application. So this demo is already on GitHub, and I will share the link in the slide. So the application is this one basically. Yeah, you have seen the future. So this is my application. It's simply microservice applications is the microservices demo that was developed by the WaveWorks team and it's a microservice application. It's basically a sock shop application with multiple services that we can use, and multiple databases. So it's it's deployed on Kubernetes, and I added support to Istio with it, and you can find it openly on GitHub. So let me remove my image so you can see perfectly. Oops, sorry. So you can see perfectly. Let me remove my camera. Yeah, so now you can see full screen. Okay, so I have my applications here already running, and let's start by exploring the observability features of Service Mesh. So here is my cluster. It contains Istio deployed into the namespace, and the application deployed in the other. So here you can see that I have multiple applications running on my cluster, and you can see that in the configuration, let me show you my configuration. Let's go to manifest, and let's pick anyone. Let's, for example, pick the catalog deployment. This is the front application, and I'm deploying only one replica. But if you come here, you can find that there are two instances that are running. And that's because the application is, I enabled this automatic sidecar injection of the envoy. So Istio by default uses envoy as the sidecar proxy. So here you find that my application is deployed alongside the proxy, which is envoy. And so the application is deployed on my sockshop namespace, and Istio is deployed on another namespace, which is I think it's Istio system, RIS, this one. I have here Istio binary, which is now no longer distributed applications. They assembled mixer and all the other components of Istio into one. So it's deployed as monolith now. So we're going back to monolith, which is a nice thing. And other great services are deployed alongside. So we have Prometheus for gathering metrics. We have Kiali, which gives nice visualization of the services that are running. We have Grafana. We have a couple of other services. So yeah, let me see. Yep, we have Grafana, and we have a couple of other services. So let's actually start with the. I've mentioned. Let's start with the observability features, and let's start exploring Prometheus. So I will do some port forwarding to access Prometheus since it's not enabled. Okay, let me go to, okay, Control A, Control A, come on, yes, you can do it. I believe I can do it. Okay, so that my application is already running, and I go to localhost 9090, and I can see I can access Prometheus. So Prometheus is up and running, and let's query for the total requests that have sent to the catalog service. So let's do that. Basically, this is the request. So I'm requesting the total request for the catalog service, and let's execute it. You see here that we have a true request of the application, and I can see the graph and see all the requests that are sent to my application. So I have, without modifying anything in our application, I have Prometheus up and running on my application. So we can connect Prometheus with Grafana, basically. Right, so let's do that, and let's port forward Grafana and see what it offers. So let's go to Grafana dashboard. Here it is. Here it's coming. It's loading. I believe it will show up right now. Okay, cool. So we have multiple dashboard that we're coming with SEO by default. We don't have to do anything. We have the service dashboard, the mesh dashboard, the galley dashboard, and performance dashboard. Let's start with the performance dashboard, and let's open the service dashboard and the mesh dashboard as well. So you can see here that we have a nice graphics of how our system is doing. You can see here some nice graph. So this is the default installation and didn't modify anything. We have here the service dashboard. So I have here some nice graphic. Let's pick another one. Let's, for example, check the shipping service. Yeah, you can see that we have some loads here. We have some the client's request volumes, the success rate, and all those kind of stuff. If we go to the service mesh dashboard, we can see here that how our mesh is basically doing. We have tracing as well with service mesh. So let's take a look at Jaeger. So if we open Jaeger, so this is Jaeger, and it will be on port. Let me copy the port here. Yep. Okay, so this is the port, and you can see that we have Jaeger UI. It's coming, so we can send many requests and check our application how it's behaving. And we have multiple. It will show us some traces of our applications. I don't know why it's taking a lot of time. Yeah, but it's back. So we have some traces of our application. If we open it, you can see how your application is behaving, and from here you can understand. If you have some your application is taking so much time for some requests, you can do some debugging and understand why your distributed system or microservices application is taking a lot of time. From here you can understand where the delay or the application why it's taking so much time and what's causing you trouble, right? And we have another component, sorry for that, and it's Kiali. I talked about it. Right, so yeah, and you can see here that's Kiali, so it's port 20. Okay, let me go here and change this one. And Kiali gives basically a nice overview of how the application is behaving, not how, but the architecture of our application and the different components and parts of my application. So the default username and password is admin. I'm too lazy to change this thing. I'm just keeping it as it is. So here we have the number of our applications. You can see here all the applications that we have. We have two namespaces. We can specify only that I want to select only the Kiali applications. So we have 7 applications here. Let's check them. Okay, we have services, Grafana, Kiali, and all those kind of stuff. If we switch to Sockshop, we can see all the applications that are running. We can see, the graph of our applications, of the graph of our application and the flow of our application. So all those stuff are basically offered and come with SEO without me doing anything. So the observability nice stuff that SEO offers, and it comes without with less with almost no code. So we talked about traffic management, and let's actually see some traffic management features of that SEO can offer. So we talked about blue-green deployments. So in my applications, if you see here, so let's deploy a new version. So if you go to my application, you could see here that I have only the one front-end applications. Where it is, I have only one front-end application. So here I want to deploy a new version of the application, and it's called V2. So it's basically the same as V1. So let me deploy it first. And if I go here, if I go back to my application, you can see that here the version is blue, and the V2 is basically the same as V1. Instead, I'm using red colors instead of blue colors. And I defined here the rules that I want how SEO or how the invoice should handle the traffic. So two important components here, the virtual service and the destination rule. So what is the virtual service and destination rule? Without going into too much details, uh, virtual service is how you route your traffic to a given destination. And destination rules is what you specify, or with destination rules, we specify what happens to traffic for that destination. So that's basically what's traffic virtual, virtual service and destination rule is. And the application, the V2 is already deployed. So let's now apply those configuration to it. So yeah, you can see that is applied. And what I said here is that, yeah, I want to deploy the application. So here the application are deployed side by side. And yeah, blue-green deployment. And now all the traffic will be routed to the red version, right? So even if the two versions are basically running, we routed the traffic to the red version, the completely. So if I go back to my service, you can see here that the V1 is still running with the V2, but I'm forwarding all the traffic to V1. What happens if I want to do some nice stuff? Let's do some Canary deployment. And here I'm saying that I want to forward 80% of the traffic to V1 and only 20% of the traffic to V2. Right, so let's run actually this deployment. And if now I refresh the page, you can see that the blue version is back. However, if I keep hitting the page, hopefully at some moment we will have the red version. So you remember it's only 20%, so we need to have a little bit of patience until we got the red version. So probably I had to increase the number because, yeah, demo gods are not with me. Please give me the red version. I want the red version. Oh, it just don't want to work. Yeah, but you got the idea. Yep. So yeah, let me try one last time. And another time, nope, it didn't work. So yeah, you got the idea. So we deployed here 20% of the traffic to V1. I still insisted to get the red one, but it didn't work. Well, it didn't work, but oh, I think I should not run. Yep, I didn't run. Okay, so my bad. I run the previous version was where all the traffic is back to V1. So now I run the Canary deployment. Sorry for that, guys. And now, yeah, I got back the red version. But if I hit again, you could see that I got more times with the blue version. Sorry for the wait, guys. I made you wait more, but what happens if I want to do some routing based on some headers? So here I want to forward all the traffic coming from Firefox to V1, and all the other browsers should have V1. I said that wrong. So forward all the traffic coming from Firefox to V2 and all other traffics to V1, right? So let me, yeah, this is the link. So now if I go back, I will have only my blue version in Chrome, right? So what happened if I want to, yeah, let me get the IP from here. Sorry for that. Let me get the IP. So this is the IP. Yeah, if I send the traffic from Chrome, you can see that from Firefox, sorry, you can see that I have the red version. Think of it as you can split the traffic by users. You can specify some users. You can specify based on some GWB token. You can specify on some elements coming from the request. So this is a great thing that we do with SEO, with traffic management, basically. Another thing that I forgot to mention is here I want to do some mirroring. And it enable us to have some confidence over the releases that we do, basically. So here, what I'm saying is all the production users will be routed to V1, but I'm routing the traffic and I'm mirroring it. I'm routing the same traffic to V2. And here checking how V2 is behaving without starting rolling it and sending the traffic to it. So this was some nice feature of traffic management. So now how about resiliency? Let's do some nice stuff. Let's add some delays. So now if I hit refresh, the application or the catalog service returns the results directly, right? So here I'm adding delay of 5 seconds. So each time the catalog service is called, it will wait 5 seconds before sending the result. So here, if I refresh, you can see that I see no catalogs. I have to wait for a couple of seconds, typically 5 seconds, until the results are back, which is a nice way if you want to start doing some nice stuff with chaos engineering and those kind of stuffs. We can do here a lot of things. We can inject abort failures. So whenever we whenever we send a request to the catalog service, we receive 500%, but only for 10% of the traffic. This is amazing for chaos engineering and those stuff. We can do some stuff for load balancing, as I have said in the presentation. There are the basics ones like round robin and those kind of stuff, but here we can define also some hashing based on some criteria, like here the source IP and those kind of stuff. We can define the retries policy, how many times I should retry before giving up on a request. So all those kind of stuff are defined in a declarative way using a YAML file, and is the job of SEO and the service mesh to apply those configuration to my application. So yeah, let's see other things. Let's basically do some, how about some rate limiting? Let's implement some rate limiting stuff, right? Okay, so yeah, this is some rate limiting. And before that, rate limiting was managed differently in SEO. So now the old way is not recommended, is entered a new, and the recommended way is deprecated. So the old way is deprecated, and the new way is using Envoy directly to use some rate limiting stuff, right? So let's basically add some rate limiting here. So let's add some rate limiting for the Envoy proxy. I'm not going over all the details here, but just showing you a small example. So I'm deploying, so I'm adding the rate limiting server here. I'm adding a rate limit service and deploying Redis with it, which will help us to implement the correct rate limiting policy for Envoy, and then deploying the rate limiting, right? And for testing, we'll be basically using Fortio. Fortio, which is a loud testing tool that plays nicely with SEO, Kubernetes and SEO. And what I will be saying, so let's first deploy Fortio, and I'm deploying it. Yep, it is deployed. Let's basically specify the Fortio pod here. It's a variable that I will need to run the tests. And finally, let's run this one, right? So what I'm saying here is that I want to execute two requests to SEO. So my policy here, my rate limiting service, I'm saying that not this one, but this one instead. Okay, not this one, not this one. Okay, should be here, right? Yep. So that's just, yeah. So this is my rate limit configuration. Sorry. So I'm having two plans, the basic plans, which allow the user to have only one request per minute, and the plus plan, which basically enables to have two requests per minute. You can have as many configuration as you want here. So I'm sending the user with the basic plan and specifying the user and hitting two requests. So we should in less than a minute. So we should have two requests in less than a minute. Basically, one should fail and the other one should pass. And this is exactly, okay, human is missing. Okay. Okay, I need to specify the HTTP. Yep. Okay, aborting because enable to create client HTTP. Okay. Oh, what is, okay, so the ingress, yes, I need the ingress EP. Sorry for that. I didn't specify the ingress IP variable, which is important. This one, I need to get it to define it. But yeah, I can define it manually, if you will. Sorry for that. I will get it from here. Yep, let me get you, right? Done. Yes, that's correct. And let's run it. So now it should run, and you should obviously say, let me add this one here. You should obviously see that one request passed and one request received 425, which basically says it's got blocked by the rate limiting. We can do other stuff with the rate limiting. We can do course policy with security stuff. We can do some MTLS, mutual TLS between our services. We can do some HTTP allocation for allow policy here. For example, for the front-end application, allow only get actions. So for the front-end catalog, allow only get actions and those kind of, so for the front-end application, allow only get to the catalog path and those kind of stuff. So a lot of stuff can be done with SEO and the service mesh that enabled us to use them easily. I hope you enjoyed the demo, and let's go back to the slide because I'm starting to go out of time. I have a lot of elements, but I will mention the repo at the end of this presentation where you can have a look and play with SEO if you want to have a quick look. I have a detailed tutorial with all the elements that you need. Okay, so we have seen the future. So now back to the question that this presentation has built upon. Do I need a service mesh? And the answer to this question is it depends. Like nearly everything in the technology space is it depends. I know you may be now very disappointed listening to me for 60 minutes now, but that's the thing, guys. I'm sorry to disappoint. It depends heavily on your needs and what's the type of your architecture. But there are some case scenarios where it makes really sense to use service mesh. starting with modernizing your existing infrastructure. So most organizations will have existing services, probably monoliths, and those monoliths will basically not be running on containers, but they could be running on VMs or even on bar machines. So service mesh will definitely help those organizations with their modernization, allowing organization to upgrade their services inventory without rewriting applications. Will enable them to adopt microservices or adopt new languages or even move into the cloud. Another important use case or amazing use case for using service mesh is when you have multiple services and many services, and you don't know how well those services are used and how well those components are behaving. So using observability features of service mesh help you to understand how is your application is behaving. Another important feature of use case, another important use case for using service meshes is pulling down an existing functionality from a monolith and create a new service from it. So service mesh can effectively help you test this functionality and check whether or not it matches the existing functionality. Another use case where service mesh will help you is to gain confidence over your releases. So if you are not confident about delivering releases to production and make it available to users, you can use traffic management features of service mesh to gain confidence over your releases. You can specify in the header only some users that are allowed to check your new version, and then when you are confident about it, you can allow some portion of the traffic to this your service. And then we are confident about the release, you can do some blue-green deployment and make it available to all your users. Another important and amazing use case of service mesh is while debugging microservices. As you probably know, debugging microservices is hard, is crazy hard. So observability features of service mesh will definitely help you to debug and understand what's going on in your mesh. And finally, adopting chaos system and chaos engineering. There is a lot of hype lately regarding chaos engineering, and adopting service mesh will help you to achieve chaos engineering in production, because that's where it should be. And you can do amazing things, as we saw in small, like as we saw in the demo. You can drop requests, you can return 500s, you can put some delay, you can return 500s, and you can do a lot of amazing stuff. And the rapid pace of change in current service mesh implementations make the costs and risks of deploying them a little bit high. And I believe that as the complexity of application increases, as you see in the picture, so service mesh becomes more and more a realistic alternative to implementing capabilities service by service. So as the service mesh technology matures, the costs and risks will probably go down, and the tipping point for adopting service mesh will get even closer. And the folks at Kinvolk did an amazing job last year benchmarking a couple of microservice architecture and adding two service mesh to it, SEO and Linkerd. And they described their experience and the cost that comes with service mesh. So there are some costs compared to the latency and the memory usage has increased while using service mesh, and even the CPU utilization. So keep in mind that service mesh is not free. There are some costs that comes with it, and you need to understand and do your own benchmarking before adopting service meshes. Think about the other costs. Think about the lock-in, and I'm talking here about the architecture lock-in. So With service mesh, we took the application logic out of the infrastructure logic, out of the application and put it into the service proxy. If the service mesh didn't work well for you, rolling back to a more previous alternative like client libraries or so could be costly. Another thing to keep in mind is the learning curve. So service mesh is a new technology, and there's a lot of things going in the service mesh ecosystem, and you have to keep up with the new stuff, and you need to make your DevOps guys and Ops guys wait for them until they master the technology before going to production and think also about the environment drift cost as well. So the final word. Should I use a service mesh? Well, it depends, as I've mentioned it. Service mesh, it brings definitely value to both monolith and microservice applications, but it comes with a cost. And you need to do your own testing and benchmarking before deciding. And my advice, if you want to start using service mesh, is to start small and then grow gradually with the service mesh. So this is the link for the demo, and there are a couple of amazing resources that helped me to build this presentation and understand better what is service mesh. So with that, I want to thank you, and I'm ready to take your questions. Thank you.
All right. I guess we have like probably 1 or 2, less minutes for the questions. And after that, you can go to the Zoom. Just remind you that you can ask questions there. All right, folks.
Yeah, let's take just one. So thank you, Mohammed, for the great details in the talk. And the first question that was asked in the channel was if suppose that there are 3 services, A, B, and C. A makes a call to B, B makes a call to C, and then the call to C times out. How does service mesh help with cascading timeouts? Like service A, which is calling to B, would it also time out? Would it start retrying it? How would you deal with this?
Yeah, so as I've said in the slides, we have like multiple services that are large sheets of functionality. The service C got like a problem and can't answer to B, so the service B keeps calling and calling until there are no threads free for this B, and then service B becomes unresponsive. So yeah, with the circuit breaking features and timeout features that the service mesh offer, we can like specify the pool freedom of connections, the max connections that we can send to and allow to be sent to that service. So if the service becomes responsive, the input process, so I'm talking about input, which return kind of it's 500 something, is 500 to the application, and the application then should know that the service C is unhealthy and it's better to B, that the application is very expensive and it could manage like you say what is the problems or some generic errors. So that's how service mesh can help in that way.
All right. I'm sorry to interrupt you. We barely hear you. Maybe we can fix that, and then afterwards in Zoom webinar you can probably repeat the answer. I guess our audience haven't heard much. But anyway, thank you for your talk. Thank you, folks, for helping with support here. Gleb and Pavel and Mohammed will with you in Zoom link. Please follow them.